Welcome back, everybody. This is a continuation of example 5.9 dealing with a fish on a fish scale in an elevator. And in the previous segment we did part A, which is finding the supporting force or the apparent weight of the fish when it is at rest, and we found that out to be 49.1. Now we're going to go to part B and find out how much is the fish going to weigh or appear to weigh when the elevator is moving upwards with an acceleration of 2.5 meters per second squared. All right, we're going to do part B and C together. We'll even try to get in part D in this one, but if not, it'll be on a separate segment. So I'm going to take those values, 2.5 meters per second squared upwards, and I'm going to rewrite it in the next frame. By the way, our salmon is 5.0 kilograms. All right, so here's our fish. I'm going to just draw it again. Maybe I can get a salmon color. Alright, there's our fish right there. Looks more like a whale, I guess, but that's okay. And it is hanging from that scale, and so there's a supporting force acting upwards. We call that supporting force the apparent weight. Force supporting, okay? That's what we want to find. That's what we want to find for part B right here, because in this scenario, in part B, the whole elevator system that the fish is in is accelerating upwards. So we can say the acceleration of the fish is going to be 2.5 meters per second squared, and that's going to be in the positive direction. All right. We also know that the mass of the fish is 5.0 kilograms. All right, and we can take that and actually turn that into a force. There's going to be a downward force, of course, of mg. Mg, mass of the fish times gravity. But the question is, what is the scale going to read if the whole fish and elevator system is accelerating upwards at 2.5 meters per second squared? All right. So once again, we are going to write a statement about the net force, or the forces on the system, on the fish system. All right. So the net force. Let's do this in black so it's a little different. The net force on the fish equals what? We can say this two different ways. Let's do the global statement first. We'll say the statement that is always true, and that is it's the mass of the fish times the acceleration of the fish. In this scenario, it's going to be upwards 2.5 meters per second squared. What's also true is that the net force on the fish is going to be equal to the sum of all the forces that are acting on it. And in this case, well, just like the last case, you've got the supporting force acting upwards. I will do that in blue. The supporting force, also known as the apparent weight, minus mg, right? Minus the weight force that is created by a gravity acting on that fish's mass. All right. Once again, we have two statements about the exact same value. These statements are equal to each other, so we can say the supporting force minus mg is going to be equal to mass of the fish times the acceleration of the fish. All right? Times acceleration of the fish. Now, this mass and this mass are basically the same thing. They are the same thing because we're talking about just the mass of the fish. I just didn't put a subscript right there. But we're going to see that these two m's are going to they're going to be the same thing. So, all right, let's solve for that supporting force, the force that is the apparent weight of the fish. So we're going to add over our mg. So supporting force is going to be mg plus mass times the acceleration of the fish, right? I'll do that right there. All right, mass of the fish. And again, we should remember that this mass refers to the fish, so that means this is the same value. What we can do to possibly make that a little bit easier is to factor it out. And I really am getting tired of changing colors right here. I'm just going to stay with black, I think. All right, mass times g plus the acceleration of the fish. In this case, the mass, well, in all cases in this scenario, it's going to be 5.0 kilograms times the quantity, 9.81, plus the acceleration of that fish, of the system. That's plus another 2.5 meters per second squared. 2.5 meters per second squared. I should have written my units in the first part. Oh well, I'll just leave them out for continuity's sake. All right, and we're going to find that the supporting force, you might see the apparent weight of the fish, is going to be greater because it's accelerating upwards. And we're adding together these accelerations right here. So 9.81 plus 2.5. Take that, multiply that by 5.0. It's going to be 61.6. 61.6 newtons. That is going to be the supporting force in part B. And if we look back and compare it to the weight force, so you might see the supporting force of the fish when it's at rest. If we go back to the previous page, right here is our weight of the fish when it's at rest. Here is our weight of the fish, or you might say the apparent weight of the fish when the elevator is accelerating upwards. So again, this the fish itself is not accelerating upwards, but it's inside this elevator, and the whole system, including the fish, has an upwards acceleration. All right. So that is part B. Let's do part C. Now I'm going to assume some things in part C that one of which is that you're okay with part B right here. We're going to find that part C is virtually the same thing, except we've got a different acceleration. So we're going to find that the supporting force, or the apparent weight, is going to be different. I'm going to start a new slide right here and redraw it again really quickly this time. All right, so here's our fish right there. It has a weight force, mg, straight down, right? It's got a supporting force, also known as apparent weight, acting upwards. And this fish has a mass of 5 kilograms. Again, this is part C right here. And the acceleration of the fish is going to be negative 3.2 meters per second squared. So it's going to be accelerating downwards. Going to be accelerating downwards. All right. So, let's see. All right, that's all we need to know. What's the first thing we do? We write a statement about the net force of the fish, right? Save a little space, I'll write over here. The net force on the fish. Our global statement is always the fact that it's mass times the acceleration of the fish. Okay? Just as true is that the net force in the fish is equal to the sum of the forces. And once again, I'm not going to do these in color. I'm just going to do them in regular old black so I can save some time. The supporting force minus mg, right? Because supporting force is acting upwards, mg is acting downwards. Let's take our two net force statements, set them equal to each other. So, mass times acceleration of the fish. You know what? I'm going to write the other one first. Sorry. I'm going to write this first here. I'll write it below. Supporting force minus mg equals mass times acceleration. Add our mg over. Looks like the exact same equation from before, right? Supporting force, also known as apparent weight, equals mass times gravity plus mass times the acceleration of the fish. What is the acceleration of the fish? It's downwards this time. So we're going to find that, especially if we factor out this m right here, g, well, g is, yeah, I'll keep g in there. G plus a. If that acceleration is negative, we're going to have a decreased acceleration. So that I think we're going to have a decreased apparent weight. So the mass of the fish is 5.0. G is 9.81. Plus, now our A is negative, so we've got to put a negative in there, plus negative 3.2 meters per second squared. That's going to mean that our supporting force, our apparent weight, is going to be the difference between 9.81 and 3.2. That times 5.0. And that gives us 33.1 newtons. Certainly less if we back up. Certainly less even than the previous values that we had when it was at rest, right here. Certainly less than when it was accelerating upwards. When it accelerates upwards, it feels heavier. When it accelerates upwards, it feels less heavy. It feels lighter. All right, I'm going to see if I can do my best to do part D in this little area here in the lower left. All right, and then we can be done with this video segment. So part D, what we're told is that, in fact, if you need to, we can go back to it just a quick. How fast, you might say, or what should the acceleration be? Sorry, must the elevator accelerative, it says. It should say how fast must the elevator accelerate such that the fish is weightless. What we're is that in part D, we're not finding the weight, we're being told the weight. And we're being told that the weight, the apparent weight, or you might say the supporting force, equals 0 newtons. 0 newtons. Okay? So the scale that is above the fish right here is going to read nothing. So what should the elevator be doing? How should the elevator be moving such that the fish has no apparent weight at all? All right? Well, once again, we're going to write a statement about the net force on the fish. Net force is going to be the mass times the acceleration of the fish. This is what we're solving for right here. What must the acceleration be in order for the supporting force to be 0? All right? It's also true is that the net force is the supporting force minus mg because they're acting in opposite directions. Let's set them equal to each other. But I'm going to write this first and then equal to that because we're solving for that acceleration. Mass times acceleration, right? Mass times acceleration of the fish, which is what we're solving for, equals the supporting force minus mg. Okay? Well, what is this? Well, I'm sorry, we need to solve for the acceleration, right? What do we do to divide by that? Or, sorry, what do we do to get rid of the m? We divide, right? So the acceleration of the fish, whatever it's going to be, is going to be the supporting force minus mg all over m. Okay? So this might look a little complicated at first because you have this this difference in the numerator and then this m in the denominator right here, but it's going to get pretty easy in just a second. What is the supporting force of the fish? Well, it's 0, right? We're told that. We're told that the fish has 0 apparent weight. So that means this part's going to be 0. So you divide 0 by anything, it's going to be 0. All right? And if you divide this part by m, what's going to happen? The m is going to cancel out, right? So that's going to become 0. So 0 minus, the m cancels out from below, 0 minus g. So what we're left with is the fact that the acceleration, why is that red? Oh, I was just writing in red. The acceleration of the fish, in order for it to feel weightless, is going to wind up to be negative g, or negative 9.81 meters per second squared. And that should make sense, because what were to happen, if here's our fish right here, all right, in the elevator, What would happen if the elevator were to suddenly go into free fall? Because that's really what this is right here, right? The elevator is in free fall. It's moving downwards at negative 9.81 meters per second squared. Well, that means there's nothing supporting it from above. Let's say the cable snapped. So everything is moving down. So you're free falling inside the elevator. So nothing is supporting you from below, nothing supporting you from above. You are essentially weightless. Now the downside to that is that there is probably a bottom to the elevator shaft and you don't want to hit the bottom. But in the meantime, you feel weightless, as this fish feels weightless as long as it's accelerating downwards at negative 9.81 meters per second squared. All right? So that's our little study into apparent weight and supporting force, which are the same thing, and a couple different examples of how to manipulate your apparent weight and supporting force. So it's example 5.9. Thanks for following along, and make sure you ask me if you have any questions. I'll see you on the next one.